Thanks, Amit, and good morning to everyone. Okay, let's talk about obfuscation. Let's not worry about the titles for now. Okay, so we know what program obfuscation is by now, and we know what virtual black box obfuscation is defined by BGIRSVYOI, and we have a lot of strong negative results for it. Okay, and there are only a handful of positive results for very limited functionalities like point functions and their extensions, unless you go to idealized models. Okay. This is completely different for indistinguishability obfuscation that changed just last year. It was defined also by BGIRSVYOI, and we have the first general purpose construction in 2013. And since then, we have had a lot of new constructions which improve upon the original construction, analyze the attack models, and so on. And there are many, many applications that use I/O now. Okay, what is I/O? Very quickly, we say that an obfuscation mechanism satisfies I/O security if for any two programs P and Q, which are functionally equivalent, the obfuscation of P looks indistinguishable from that of Q. Okay, and now the key property here is that the two programs have to be identical. And this is really the problem. If you've been paying attention for the last few days, you realize that I/O doesn't really give you any hiding guarantees. So it is very hard to make sense of it. Like, even if we achieve I/O, what can we do with it? And at the face of it, it looks very useless. But in this past 2 years, we have seen many, many constructions which use I/O and achieve new results. And all of the talks I see that many of these constructions are very, very complex. And the reason is that I/O doesn't really hide anything. So you have to come up with new techniques to hide the information you want that you're utilizing in your program. And there are only very handful of techniques like puncturing, two-key paradigm, and some complex combination of these two. Okay, so this brings us to the question, is there a model of, now we have I/O, is there a model of I/O that is slightly more useful than I/O which can simplify our constructions, for example? Okay? And one such approach was, for example, differing inputs obfuscation, which is also defined by BGIRSVYOI, where instead of requiring the two programs P and Q to be identical, we slightly relax the condition and require that the obfuscation mechanism also maintains indistinguishability even if the two programs are not identical, merely they look identical. So for any polynomial time algorithm, if it is hard to find a differing input, then the obfuscation of two programs should look indistinguishable. Okay. But if the programs were fixed in advance, then clearly you cannot satisfy this, so you have to define the notion of a sampler over programs. So we say that a sampling algorithm SAM for two programs P and Q, it is a good sampling algorithm or a differing input sampler if for every circuit of polynomial size, for every set of efficient algorithms, it is hard to find a differing input X to the programs that were sampled by the sampler. Okay? So this is the notion of a differing input sampler, and I want you to pay attention to these two entities here. The sampler has random coins R, but the same coins are not provided as auxiliary input to the attacking algorithm. So the sampler can choose to output any auxiliary information, and that is the auxiliary information that attacking circuit has to use to find a differing input. Okay, so this is the existing notion of DIO. And then DIO security says, DIO obfuscation says that these two distributions should look computationally indistinguishable, where in addition to the obfuscation of the programs, the distinguisher also gets as input the auxiliary input. Okay, this is the DIO security requirement, and once again, even if the sampler might have used very different random coins to sample the two programs P and Q, that is not what the distinguishing algorithm gets as input. Okay, this is a key point in this definition. And other than that, we have the usual correctness and efficiency requirements that I'm not going to go into. Okay, and as Stefano brilliantly explained yesterday, for auxiliary input obfuscation, this auxiliary input is actually source of a lot of troubles. And Gerg et al. Demonstrated a concrete assumption on obfuscation, such that if you believe that assumption, then you can actually rule out the existence of DIO, in particular with respect to general auxiliary input. And we have seen from many examples in the past that auxiliary input can be a source of a lot of troubles. In particular, Stefano was ruling out the existence of Diffie-Hellman, the DDH problem, auxiliary input DDH problem, if you give me VGB obfuscation. Okay, so if you believe in obfuscation, then you can formulate assumptions which imply implausibility of some other DIO type assumptions. Okay, so this really brings us back to where we were. Either we believe in I/O and continue with all these complex constructions, which is great, of course, if you can do that. But in certain situations, it is just not possible to do. So you really have to rely on DIO. So then what do we do with this auxiliary input? We can get rid of them. But in that case, it's not clear whether it is going to be any more useful than I/O. Okay? The other option is that you can just complain that all of these negative results, they work with a very contrived type of auxiliary information. But for your application, maybe this assumption still holds. And it would work until someone breaks it. But you will also end up with a disparate set of assumptions for which there is no real understanding of why it should be secure. So in particular, it leaves the possibility of finding a notion of obfuscation which is concise enough that you can study, so that if you prove an implausibility result for that particular notion, you would hope that at least it will expose some weaknesses in your obfuscation mechanism rather than be an artifact of your definition. Okay? And this is where our work comes in. We try to look at how exactly the auxiliary information is used in current negative results and try to sort of attack the problem at the root, so that hopefully there is no funny interaction going on between auxiliary input and the execution of the program, which you can exploit to rule out the existence of such DIO. Okay? And if you look at all these negative results, really all of them work by keeping some kind of secret in auxiliary information. In particular, the work that was very relevant to our work, in this work, auxiliary information is just an obfuscated code, such that if I give you the code, it is not possible for you to extract a differing input to the programs. However, it is enough for you to distinguish. Okay? So, and even if you look at all the previous results in this direction, like Boyle and Pass and Butansky et al., they all work by keeping some kind of secret information in the obfuscated code. So that is the first thing I want to rule out. And if I can rule that out, hopefully I'll end up with a notion that is plausible and concise and is still useful. Okay? So this is where public coin DIO comes in. It simply removes the ability to keep any secrets in the auxiliary information. In particular, whatever random coins the sampler used to sample the two programs, that is the only auxiliary information allowed to the attacking algorithm and to the distinguisher. And the idea is that if the sampler itself couldn't find two inputs which allow you to distinguish between the two programs, then if you can really distinguish between the challenge obfuscations, you must somehow break obfuscation rather than rely on using auxiliary information. Okay? So let me start by defining it. As before, we will define a differing input sampler, but now it will be public coin, where we have the sampling algorithm as before. It's going to output two circuits P and Q. But there is no auxiliary information anymore here. Instead, the attacking algorithm simply gets the coins of the sampling algorithm. And then we require that even then it should be hard to find such inputs. One example would be, for example, collision-resistant hash functions. If the sampling algorithm is outputting programs which may have different behavior if you found collisions, then so be it. Even the sampling algorithm cannot find such an input, so yeah.
So the ANR, in the previous case it was Z.
Yeah, so instead of instead of giving the randomness of sampler as input, it could have, for example, given whatever auxiliary information SAM outputs.
He was carrying more information about the code which...
No, for example, if the SAM wanted, it could output one-way function of R, right? And there is no way to recover R. So it's strictly less because
I'm just trying to understand the difference.
Sure. So in this case, okay, clearly the attacker can depend on the sampler. Yes. And if I give him R, it has all the information that the sampler has, right? But if it was Z, then sampler can keep some secret coins from the attacking algorithm. Okay. So, okay. So as before, we have the notion of public coin differing input sampler, and now we say, okay, and I already explained you this. So now the notion of public coin DIO, it is just the same as original DIO notion, except that you are only working with public coin differing input samplers. Okay? And in particular, pay attention to this part. It is not Z anymore. The distinguishing algorithm gets the same coins as input as the sampler.
Can you just, sorry, once again, previous the definition. The adversary is still non-uniform.
Yes.
So earlier you said that the Z cannot depend on the R, the auxiliary information in the original definition.
No, it could. Why it can? Of course, yeah. Sampler is outputting Z, right? So.
But the sampler is outputting Z.
Yeah. Okay, so
Essentially, you're saying that the sampler doesn't know the pointers, right?
No, in particular, if you look at the negative results, in those negative results, if I tell you all the coins that the sampler used to sample the auxiliary information, you would be able to find a differing input.
Exactly.
And that is what I want to rule out here.
The sampler does know a point where the two programs are different.
Yes.
In your case, the sampler doesn't.
Yeah, those results are not allowed. Yeah. Yeah.
Basically, Z is fully informative about R. That's
No, you don't know that. If I give you a compressing function of R.
making Z more informative about R.
No, how is Z more information? I processed R to get Z.
I think he's saying in this definition.
Yes, in this definition.
Equals R.
Z equals R.
Yes, sure.
It's formative about R.
Okay.
Equals R.
Okay, yeah. If you said auxiliary information, then I'll say yes.
That will be good.
Yes.
Okay. Okay, and I just want to say a few things that in defining this notion, we are just following what has been there before. We are not doing something new. I mean, we are doing something new, but we are driving inspiration from previous works on this as well. So first of all, as I said before, this notion is plausible because there is no secrets in the auxiliary input. So none of the existing results work, so that's good. So we have a plausible notion, first of all. But why should we believe it any more than just assuming that it is good for your distribution? Well, for these distributions, as I said before, there is no real understanding. Whereas if you look at, so all of these negative results, they also have a consequence to extraction assumptions, like knowledge of exponent assumptions or snarks and so on. So if you define an auxiliary input version of these notions, they will be affected also by the GGHW result. Unless you do what was done back in 92 and 2004, where you only allow randomness as the auxiliary information. For that, there are no attacks. For that, there are no implausibility result. And this assumption has been there for a long time. It has been analyzed. So we are in good shoes. If you prove an implausibility result for public key in DIO, our hope is really that you will expose some weaknesses in the obfuscation mechanism rather than just exploiting the definitional information out there. Okay. So, and it is also better than assuming benign distribution. So you cannot, if you just assume uniform distribution over auxiliary information, that's also not okay, because it might still be possible to keep secrets, which will allow the sampler to somehow find a differing input, whereas the distinguishing algorithm might not be able to exploit such an input. So you really need to rule out the possibility of any secret coins rather than just assuming benign distribution which look harmless. Okay. So now you have this notion. The next question is it too weak? By requiring the information to be public coin, maybe in your hybrid arguments you won't be able to use it anymore. Okay? So what we can show is that you can recover the bootstrapping theorem that has been there for DIO. In particular, if you give me a public coin DIO for NC1 and fully homomorphic encryption and snarks, then I can give you succinct public coin DIO for Turing machines, and I don't have to assume any kind of bound on the input length. And as I pointed out before, all of these negative results about DIO, they also impact extractability assumptions such as snarks. So for this result, it is very important that we only work with the public coin formulation of snark, where the auxiliary information is just the randomness of the adversary. So the only candidate for such a construction is Micali's CS proofs, so this result has to assume that Micali's CS proofs are secure. Okay. Now using the first result, I can also give you succinct functional encryption for Turing machines. Now these things are already known, let me tell you, right? But not for Turing machines with unbounded input. But my goal here is, it is only selectively secure, but my goal here is not to provide a feasibility result, but just to show that public coin DIO is actually useful, more than you would think. It's not completely useless. Because it really looks like, oh, if the auxiliary information is just uniformly random string that has no secrets, how can you use it? It's like having no auxiliary input at all. So,
let me just make sure. This notion still implies I/O, right? DIO.
yes, of course. Yeah, because there are no differing inputs. So,
Given that I/O was useful, DIO is also useful. So the question is the proof simple? So even for this second result, is the proof simpler, or then I/O you kind of skip some step? Or
no, first of all, you don't have this result if you don't assume DIO, some form of DIO. Not anymore? Okay. Okay, so apparently there is some new result which hopefully gets you this. But yes, this is hopefully much simpler also. Yes, that is also true.
Also in terms of the assumption, if I had to bet if one of the two things is true, okay, so there is a quantitative aspect of the sub-exponential security versus polynomial security. So for public coin DIO, we only need polynomial security, whereas all of the recent techniques that exploit, in this domain, they all rely on sub-exponential I/O. So it's kind of like, what do you prefer, sub-exponential one-way function or polynomial time trapdoor permutation, right, in the old days. So again, we kind of forget the sub-exponential, but sub-exponential I/O versus public on the I/O, that's an aesthetic choice, but they're technically incomparable assumption. It's not, certainly not worse.
Okay. And the construction is also much simpler, but it is more complex than the previous constructions, which were only for circuits. Because the auxiliary information is public coin, so you really have to be more careful in hybrids.
Well, but I guess my question is, even for things which were known from I/O, I'm saying an example where the I/O would shape one of
Yes.
them would be useful. So do you have?
Yes, you will see. So for example, I'll show you a non-black box simulation technique, where you would see I'll just simply replace the universal argument with the obfuscation of a Turing machine. And I'll just hide some information, and this information is never seen if you cannot find collisions in the hash function. Whereas with I/O, I cannot do that. Yeah. Okay, so this is what I was mentioning, that you can go all the way to concurrent zero knowledge. Using this result, we can get fully concurrent zero knowledge also. So, and it is a new non-black box technique, which simply exploits obfuscation instead of doing universal arguments. Okay. So let me talk a little bit about the construction for Turing machines. And this is, again, just to give you a flavor of how the construction would go and how the proof might go. I will not go into too much detail, but just to give you a flavor of why public coin is still sufficient. Okay, so everybody knows what functional encryption is, so I'm not going to go into that. We are only going to work with selective security. So the adversary will announce the two strings x0 and x1 in the beginning, and later on he will ask for keys for Turing machines. Okay? And because we are dealing with Turing machines and there is no a priori fixed bound on size of x0 and x1, so unlike previous techniques, x0 and x1 cannot go into the public parameters. So we have to be careful about that. Did you have a question? Okay, sorry.
This is the definition of...
Indistinguishability-based functional encryption for Turing machines. Say it again, sorry?
With selective security.
Yeah, with selective security, yes.
So can you explain in your diagram here where the selective, what's selective?
The bits that will be encrypted have been announced in the beginning, even before you see public parameters. Okay. So the construction, the setup, we are going to have, first of all, 3 public keys. So in the previous constructions, you saw 2 public keys where you exploited 2-key paradigm. But here we need 3 public keys because we'll have to extract a string which finds collisions in the hash function. That is what PK3 is for. Okay, we will have 2 strings alpha and alpha 2. Each one of them is a commitment to 0 string, fresh commitment to 0 string. And then, as before, we will have a hash function and a CRS for Nizic proofs. The master secret key is going to be the secret key for the first public key. What about encryption? First of all, you will encrypt as before under the first 2 public keys, the same value x. And then under C3, you will encrypt everything you have known so far. In particular, you will encrypt the value x and the randomness that you used in the first 2 encryption. And don't worry about the format for now. Okay? And then you will give a Nizic proof about the correctness of C1, C2, and C3. So what will you prove? So here is the ciphertext from the previous slide. You will prove that there is randomness R3 and a string A of this format where, first of all, A is encrypted under C3. And second, in C1, C2, either you're encrypting the same value, or if you're not encrypting the same value, then the hash of both of these values appears in alpha 1 and alpha 2. So alpha 1 is a commitment to hash of x1, and alpha 2 is a commitment to hash of x2.
What is alpha 1? That is not alpha 1.
It's in the public parameters. Okay. What about key generation? It's simple, as you would expect. You will just give an obfuscation of a program, which...
Can you go back 2 slides?
You two keep going.
The randomness for the computation. It's at the bottom.
Oh, U1 and U2. Yeah, that's just a randomness for U1, alpha 1 and alpha 2.
J is a commitment to hash of xj.
Yes, where J is in 1 and 2. Okay. Yeah, don't focus on literals and... yeah, you don't have to match I and J because it's slightly more useful when you're proving. So I don't have to necessarily bind alpha 1 to x1 and alpha 2 to x2 if I do it this way. That's why I'm not setting J equals to I. But yeah, one of them is a commitment to x1 and the other one is a commitment to x2. So
actually, now I lost track. So x1 and x2 are
the two strings announced in the beginning, for which we are proving security. It's selectively secure, so.
right, but the construction, presumably you're going to use it not only in that game where x1 and x2.
Right, so an honest encryptor will never have to worry about this because he's always encrypting the same values, right?
Oh, I see. X1 and X2 are not quantified outside the proof. They're under the existential quantifier.
Right. I mean, X1 and X2 exist because encryption is binding and the format has been fixed here. So this statement is also well defined. NP statement is also not dependent on public parameters necessarily, right?
Right.
Yeah.
That was the part I didn't parse properly.
Okay. Key generation is simply an obfuscation of a program which evaluates the Turing machine after decrypting C1, but before that it'll just verify that the proof is correct, and here we are just going to use public ONDIO for Turing machines. Okay, so here is the program, and decryption is you simply run this program on the ciphertext. Okay, so here is a high-level idea of proof sketch. Yeah, sorry. Okay.
I feel you're going too fast here.
Oh, okay. Well, the reason is that the construction is very, very similar to previous constructions. The key point is this hash function and PK3. So other than that...
So when you say previous constructions... So
for example, BGIRSVYOI, where you use statistically sound NIZK, where there is only one theorem for which this NIZK is false.
You're saying something negative about DIO, right? So you're saying there was a simple construction...
No. Okay, let's step back. No, let's step back. For BGIRSVYOI, there was a construction for functional encryption for circuits, not for Turing machines. Okay, so here I'm clearly getting something more, but obviously I have to pay somewhere, right?
But so in the previous thing, you don't know how to extend to the second, right?
No, in fact, the proof techniques by itself fails, and you have to rely on, because you have to rely on public ONDIO. Yeah. But the ideas for switching from SK1 to SK2, and those ideas are very similar, so that's why I'm going too fast, I guess. Okay, so here are the public parameters. This is how encryption looked like, and this is what the secret key looked like. Okay, and we are going to go from encryption of x1 to encryption of x2 to prove security. Everything else will remain the same. And for all Turing machines M of x1 is going to be equal to M of x2. So in the first part, I'm going to change alpha 1 and alpha 2. In particular, I know x1 and x2 in the beginning, so I can set alpha 1 to be a commitment of hash of x1, and alpha 2 to be a commitment of hash of x2, and this change looks indistinguishable. And in particular, once I have made this change, I can, if I wanted to, prove a quote-unquote false statement. It's not really false because I know a witness, but I can get away with encrypting two different values. Okay? So the proof is statistically sound. Okay, so in the second part, I'm going to change x1 to x2. As a result, this is also going to change, my witness, and this is going to change C3 also, my encryption. Okay? Before I do that, oops. But the good part is that we can rely on a strong non-interactive witness indistinguishability. So even if there is only one witness, because the statements look indistinguishable, this part is also easily argued. Okay, nothing new here. Great.
Is pi still true?
Yeah, pi is still true. Because I will use the fact that alpha 1 is indeed a commitment to hash of x1 and alpha 2 to hash of x2.
But what is a pi? How do you generate pi? What witness do you use to generate pi?
Hash of x1 and hash of x2 along with the randomness used to. Yeah. That's the first thing I did. Yeah. Okay, and now I'm going to switch SK1 to SK2. This is okay because M of x1 is equal to M of x2. And in particular, this is where the hash function is being used. In particular, if there is an adversary who can distinguish this change, then you can extract a ciphertext which will have this particular structure. It will have C1, C2, and C3, and the proof will be correct. So if he did not encrypt either x1 here or x2 here, or any value different from x1 and x2, then it must imply that hash of one of those two strings is committed in alpha 1 or alpha 2. But I already fixed alpha 1 alpha 2 to hash of x1 and a hash of x2. And since one of these two values is at least different from both x1 and x2, I would have found a collision. And I can extract such a collision because I know secret key for PK3. That was the entire role of PK3. Okay. Now let me give you another example. Is that okay, or? Oh, that's all? Okay, very quickly. So let me just quickly show you how I can avoid universal arguments in Barak's protocol, which is a straight line zero knowledge. and not the concurrent zero knowledge part, only the straight line zero knowledge part. Okay, so very quickly you have prover and verifier, where you have the first preamble of 3 rounds where the hash function is sent by the verifier. The prover will commit to some random string or 0, and the verifier will respond with R. And then they run an encrypted universal argument where the prover proves that it knows a program which could have predicted R. And then in the end, there's a witness indistinguishable proof about X, or success in encrypted argument. Okay? And you prove simulation by just using V***'s code. Now, this is the part I want to remove. And as I was saying earlier, you can simply replace it by the obfuscation of the following Turing machine. It accepts as input a program, and all the witnesses, all the random strings and everything that you were going to use in the encrypted universal argument. And it verifies all of those things that you were proving in the encrypted UARG, and if so, then it will output the secret. And now you can see, Evgeny, that there is a secret value M, right? And there are no 2-key paradigm, there is no puncturing going on here. Yeah?
Does that mean that this obfuscation is a universal argument?
No, this is an obfuscation of just a Turing machine, which accepts a program as input, verifies.
Does it give you a sort of generic way to build universal arguments?
I haven't thought about that. Yeah. Because, I mean, there might be things like extraction and so on. So for soundness, we do rely on DIO property. So then maybe something like that will show up in the proof. But here it's okay because we are only relying on, we are using DIO only for soundness, not for zero knowledge. Okay.
Why is the public point here? I just want to make sure.
That's a little tricky to see, but the only thing in the end, so for this part to work, right, you only need to prove that you cannot extract a witness which will allow you to learn M. And for that, all that really matters is that this part, you cannot succeed in this part. But even if you had a witness to X, you will never be able to succeed in this part. That you can just derive from Barak's protocol as long as H is collision resistant. Okay? And that only relies on the public coin property. So no matter what secret you know about the verifier, you can still conclude this, and therefore you can rely on this. So.
Your knowledge proofs if you use PCDIO, and you no longer have the bound on the witness side.
Can you repeat that?
Okay. So as I was saying, again to Evgeny, I guess this is indistinguishable from a dummy program which simply outputs bot, right? And then it'll have no information about M, and therefore you can prove soundness. Okay. So again, key points here. For this construction to work, you must use Turing machines, obfuscation for Turing machines, because there is no a priori bound on how big V* is. Public coin DIO is sufficient, and you actually get an explicit simulator, which is unlike knowledge of exponent-based assumption constructions, where you only get an existential result, but you don't get an actual simulator that you can run. But here you do get a simulator. Okay?
So DIO is only used as a proof?
Only for soundness. And finally, this simple protocol does not give you concurrent zero knowledge, but it is actually possible to make it concurrent zero knowledge based on these techniques. And finally, very recently, Chung, Lin, and Pass, they do get concurrent zero knowledge under sub-exponential I/O. So, constant round concurrent zero. You don't need sub-exponential? Okay. So, great.
Does not extend to concurrent zero knowledge?
The simple protocol that I told you, and the simulator, because you can, instead of using V* code, you could have just, but that does not extend because the running time keeps increasing, so it will become exponential very quickly. So you have to rely on DGS Oracle, that once you have extracted a trapdoor, you never extract it again. So you commit an Oracle program.
So the point of the bullet is that it can be extended to.
Yes. No, it depends on how you see it. The technique can be extended, but that particular protocol and the simulator does not extend to.
With modifications.
Yes.
Yeah, right. Like, this is not an open problem, right? Yeah. All right.
Okay. Well, it was until, I guess, this. Okay. That's all I have to say.